So yeah, I come from the Idiap Research Institute. It's a small research institute in the Swiss Alps, about 200 people working in the field of machine learning and AI. Nowadays, when we say that we are working in AI, it doesn't mean so much, but for us it means something because we have been doing that for more than 30 years. So from the beginning of the institute, the specialization was AI. And in this research place, I'm heading a group called Robot Learning and Interaction. We are also affiliated with EPFL in Lausanne, so we have PhD students who have both the affiliation with Idiap and with EPFL. So in my group, we would like to transfer skills, and manipulation skills in particular. When I'm saying transferring, it means a robot that can learn by imitating people. But it doesn't mean that we only record the trajectory and that we will replay the same trajectory on the robot. What we would like to do is to have robots being able to understand how to adapt themselves to new environments and situations. So if I would like my robot to carry a box, ideally I would like that if I'm changing the size of the box, that my robot is smart enough in order to adapt to these different tools and objects that it needs to handle. And also, ideally, if I decide to change the robot, I would like the same skill to be transferred from one machine to the other. Maybe not all the skills, but at least part of it. Some part that will be invariant, that are valid for both platforms. So the challenges behind will be about adaptation. And when I'm talking about learning from demonstration, it's about learning what are these sensory motor skills that we would like our robots to have. And we are specialized in manipulation skills. So this is typically the kind of experiments that we do in our lab, either with multiple robots, so we care about bimanual skills, how to coordinate multiple limbs, and we care also about viewing the robot as a whole body manipulator. So, you know, like mathematically, it's more simple to think of the robot as a single point moving in space. But in reality, you have this kinematic chain, this arm, where we can control the robot at the level of the joints. And also, this robot has multiple possible contact points. So in our group, we are interested in thinking of the robot as the full kinematic chain, with here, like, capability, like handling objects that can be maybe bulkier objects by having the robot deciding which contact point to use along the robot body. And we believe that typically for humanoid robots, this is something that is very important because we have these robots having very simple hands, and we need to consider also the forearms if we want them to manipulate objects in the environment in a skillful way. We also care about robots deciding when to use tools and in which way to grasp tools. Here in this case, if we have objects that are far away, we have a robot that can use a tool to bring the object closer. And we don't pre-program this, it's the robot deciding, depending on what it needs to do, like which tool to use and also how to grab the tool, at which part of the tool it should grab it in order to be efficient. We did also some experiment with the robot hammering a nail, and here it's very important that we grasp the tool in the correct way if we want to be efficient at using the tool. So this is for prehensile manipulation. But we also care about non-prehensile manipulation. It's a term that we use to describe what the robot can do without necessarily using the gripper, but for example, pushing objects, pushing objects, so more generally exploiting the workspace, exploiting physics, exploiting the surfaces that is in front of the robot in order to manipulate objects more efficiently. So it can be typically separating objects, so that they can be grabbed more easily. It can be sorting objects, like making piles of objects. It can also be sliding objects on the border of a table so that it's graspable. It's a skill that we are all using all the time, and sometimes we don't realize how much we are using this. We are always like sliding and pushing objects, also sometimes directly within our hands, in order to reconfigure an object within our hands. And for robots, it's a difficult skill, and we need research to do this and to have the robot being able to do that in an autonomous way. So typically, if you have the robot holding a tool, how the robot can also slide it if it wants to reconfigure the tool in a different way. So this is for pushing and pulling. That's the most basic form of exploiting the environment. But we are also tackling this kind of skill that is using this time multiple surfaces that can also be vertical. That is useful if you want to tilt a box, for example. So in this video, you have an object that is in a given configuration. You would like to bring it in another configuration with a different orientation, and you have the robot that needs to figure out, can I use these different elements in the workspace to help me achieve this in an efficient way? So it's a combination of different movement behaviors, like pushing, tilting the object, and pulling it back to the desired location. And the last example I showed here is more like a playful example, but that I think is really important, is to have the robot being able to both anticipate and be reactive. And this is a challenge also that we have in manipulation skills. It's to combine the two in an efficient way. If you have a robot being purely reactive, it cannot really predict or anticipate what will happen. While if you do a robot being only anticipative or playing a trajectory in an open loop fashion, then it cannot correct something that would happen that has not been, that is not known in advance. So we need to have a good balance between these reactive and anticipative behaviors if we want to produce movements that are skillful. And here the skill was to play this hierarchy game against another robot. So in this challenge, we had teams who were programming one robot, and then at the event, the different teams were competing with an autonomous machine that didn't know about what the others have programmed, and we needed this kind of reactivity and anticipation in order to win the game. Other examples of non-prehensile manipulation are the dynamic movements. Here with examples that are related to throwing and catching, with an experiment that we did a few years back that was combining learning from demonstration and reinforcement learning as a way for the robot to acquire this kind of skills that can then be very repetitive in the sense that these machines are very precise. So if we have understood how to connect the sensory information to the motor actions, then the robot can make that in a very long way. Here we let it run for more than 1 hour, and there was no mistake happening after the robot has learned this skill. And finally, we are in Switzerland, so we have also a lot of watch manufacturers that cares about very tiny movements, about very precise and small movements. So we have also a line of work in this direction, where here our goal is to use, I would say, standard robots and to try to push the limits of these robots so that they can be more precise than what we see in the specs of the robot, in the data sheets. And the way we do this is to copy what humans do. You know, like we are not really precise. Like if I'm closing my eyes and I'm trying to do a task like this, I might fail to do it. So I'm not precise if I'm not using the sensory feedback. And with robots, we can do something similar. Like if we have a sensor, in this case, it's a sensor that is mounted on another robot and that can move, so it's also like active sensing. We can actually cope with we can compensate for the errors of the robot and only correct what is missing in order to make a very precise insertion task. Here it's to put a thread into the needle, the head of a needle. And it's mimicking some task that is used in watch manufacturing with more specialized components. So these examples are about robots that we would like to act on their own. So here the target is to have robots that would be autonomous. But we have also other applications that are closer to human-robot collaboration, that is this time targeting both the user and the robot to work together. And for that, we have different ways of treating the problem. It can either be to view the robot as a tool, where some motors will be controlled autonomously by the robot, and where the user can still work together with the robot, and sometimes physically. Here in this example, the user is moving this tool, and the robot is doing some part of the task. And here the part of the task that it needs to do is first to compensate for the gravity effect, so that the user doesn't feel that the robot is heavy, and also to point at an object. So here in this example, it's very useful for the user because you always have the robot pointing toward the object of interest. So if you imagine that if we would have a tool like a sensor, for example, looking at this specific object, then the user doesn't need to care about this orientation aspect. This is something that will be autonomously produced by the robot, while the user can still move the robot the way he or she wants. So this principle is often called like virtual guidance, or it can be called also virtual guides is one of the terms, or kinesthetic teaching is another term that we use for that. And similarly to this shared control paradigm, we have the teleoperation task, where here the user is teleoperating the robot, possibly at distance. In this project, we were teleoperating a robot that was manipulating valves underwater. So it was an underwater robot with 2 arms, and we had the teleoperation center, so a lot of hardware here to be considered. And what we wanted to have is the robot being semi-autonomous, in the sense that the teleoperator should not care about everything that is happening remotely. Like for example, if we have like perturbations underwater, the user doesn't need really to correct that. If you have a robot helping at doing this correction autonomously, then we have a shared control principle where the teleoperator doesn't need to care about all of the details. Here the robot is autonomously aligning the gripper toward the valve, and for the user, everything in the simulated environment will be static, and it will be much easier to demonstrate what to do by moving from one valve to another, while on the other side there is a control loop that will be much faster and that will cope with perturbations that can happen. So when we do this kind of experiments, we first test in the lab. So here this video is showing what we do in the lab. So that's typically the kind of mock-up that we have in our lab with 2 robots. So one will be as if it was the teleoperation center. This other robot will be acting as the remote robot. And here what you see is that the valves are placed differently on one side and the other. And the user here decides which valve to turn. And on the other side there is this kind of autonomous mapping from this situation to this other situation, where the user doesn't need to look at on this side. The user doesn't care. The user is just like showing what to do. And on the other side, there is this automatic adaptation to a different situation here with different configurations of valves. So in all of these examples, there are some elements of control, optimization, and also machine learning. But machine learning in our group, we are very careful about what to use. Like personally, this is the way I see machine learning nowadays. Very aggressive use of huge amount of data with a lot of, I would say, passive observation of this data. And for what we want to do with a robot, it's too difficult to use these systems. In some applications, it's fine. Like if the data set is already here, if also the task is well defined, then it's all right to use this huge amount of data. But the problem we have with robotics is often that we have many platforms, so it's hard to transfer tasks from one platform to another, because it can be like different organization of the joint, different degrees of freedom that you have to control your robot. There is also a wide variety of tasks that we would like these robots to do. It's not as well defined as if you generate an image or you generate text. We might not know in advance what's the task to be done. The range is too large to really have these data sets to be easily accessed. And then we have also a lot of users. So if it's like human-robot collaboration, there will be a lot of user preferences that we need to take into account. So we have a problem that is, I would say, quite different to the standard machine learning problem. It's more about having the human in the loop. It's like human in the loop learning. The keywords I prefer to use is interaction, curriculum learning, active learning. It's also combining different skill acquisition strategies. Here, this figure here is showing like what we can do as strategies to refine some task or some skill. So we can, of course, have the robot trying on its own, like having reinforcement learning, self-refinement mechanisms. If we do that, we need to be careful that what we simulate is not necessarily what we can run on the real platform. So if we would like a robot to learn by trial and errors, by using the real hardware, it might take a huge amount of time. So we need to be careful about the way these robots will use the trials that they do and in order to refine the task. So sometimes we take a bit too much the shortcut of saying if it's simulated, we can let it run for days, weeks, or more. But I would argue that if we want to scale to really rich manipulation skills, we should think much more about the algorithm and be careful about each sample that the robot is generating in order to learn some task. And the robot is not alone, so we can guide it. So we can also help the robot to learn these skills. And here there are many ways to help the robot. We can first put it in situations that is easy to learn at the beginning, and when the robot is progressing, we can make the situation harder and harder. So we can have some form of curriculum learning. That is also what we do with our children. Like the way we teach at school, it's similar. Like we start from simple examples and we make it more and more complex so that the full pipeline is allowing to understand quite complex principles. And for a robot, it's the same. We need to put it in a situation that is first easy and progressively increase the complexity level of the situation that the robot has to face as a manipulation task. The user can also be here to demonstrate directly, so to have the robot learning by imitation. And when we talk about imitation, there is not only one way of imitating, and we are actually using many different ways. We can, for example, copy the actions. So this is useful for tasks where we maybe don't understand what's the underlying goals, but we just copy in some way blindly, like we mimic the actions of someone else. And by doing this, we can, we can have this kind of blind copying that might be later useful to do like more complex tasks. The other way is to understand what the person is doing and try to copy only the underlying goals behind the actions. And it's sometimes called emulation. Here it means it's more cognitive, like we need to understand what was the purpose of the task. And when we have understand that, we will replicate this purpose and possibly using very different actions. So it's typically the example of maybe seeing someone putting a pot on a shelf that is high, and then maybe having a child understanding that maybe by taking a chair, the child can do the same thing, even if the height is different. So here that would be goal emulation. And often we noticed that we need a combination of this. Like goal emulation, it looks as if it's more like high level, I would say, behavior. But the problem with this is if you want to learn a task where you cannot directly see the outcome, then this is becoming complicated to only use goal emulation. So often we need the combination of the two. And the image I like to show, to think about this process is this one. It's called sometimes the scaffolding process. And scaffolding means here that we need to put some scaffolds for the robot to learn. So it can be this kind of support that we have. If we think of building a house, at the beginning we need a lot of these scaffolds. But once we construct the house, we can progressively remove the scaffolds. And ideally, at the end, we would like our house to stand on its own without the scaffold. And for a robot, it's the same. Like maybe the user is here at the beginning for quite some time, but if there are repetitive patterns, if there are things recurring where the robot can observe enough data, then we can progressively remove this support and ideally having at the end the robot being at least more autonomous or helping, assisting the person with more skillful manipulation tasks. Okay, now in my work we often use the term frugal learning. So it's to distinguish ourselves to the standard, I would say, machine learning field. And frugal learning means two things. It means frugal in the amount of data that we require, and it also means frugality in what needs to be learned. Because there is often a mistake in robotics. It's to, I would say, to not think enough about what needs to be learned. Because there are many things that we know about in terms of control theory, or in terms of representations. So we have a lot of these prior knowledge that we can inject. We can sometimes call this also inductive bias as a learning problem. And it means that if we introduce what we know about the world, what we know about geometry, what we know about control, then it's very likely that the robot doesn't need to learn everything, but that can rely on a lot of these principles that we know about. So frugality in this case means that we really need to take one step back and think about what really needs to be learned, and have a robot learning only these aspects that we cannot model in some way, that are too hard to model because there are too much uncertainty in the system. So that's one important aspect, is to think of the learning algorithms. And another important aspect is to think of the interfaces, like how to have this human-in-the-loop learning process happening. And here I wanted to show this work that was in collaboration with Daniel and Frédéric a few years back, that was about thinking of the way we can demonstrate trajectories to a robot, like movements. How can we actually edit movements, and how can we craft interfaces that would allow to edit these movements? So we took as a baseline the concept of splines, as we see in a computer drawing program, where we can draw paths easily by using key points and by using a set of via points like this in order to draw curves. But then we wanted to introduce some element of variability, because when we have a robot moving in the real world, it can get pretty boring if the robot is always doing the same thing. While if we think of movements, there are a lot of variations that are possible. Movements that can be really, like I would say, functional movements, like when we pick an object to put it somewhere else, but also movement like drawing. There are variations. Some variations are not possible, some variations are. And we wanted to have an interface that could let the user decide about this. So here the principle is relatively simple. It's to provide, instead of providing like simple key points, it's also to provide the variations that we want around these key points. So these ellipses that you see are depicting what kind of variations we have for each of the key points. And moving these ellipses is easy because you have these axes, and you can move this in an easy way, and you can observe actually like multiple generation of trajectories that would fit with this kind of coordination and variation patterns that we provide. And we tested that on the real robot with different experiments related to graffiti art, and also here some trials with light painting in order to exploit this interface. And I think Daniel will also come back to this point in his presentation. Okay, so now the topic I would like to discuss is something that has been like motivating us recently. Like we have this problem that is an optimal control problem that is called ergodic control, and we find it really fascinating, and there are a lot of research to be done in this direction. You know, when we combine learning and control, what most research groups will do is to think of the problem as learning how to control the robot. But the opposite is rarely investigated, which is how to move if we want a robot to learn, how to explore. And here it's depicted in this image by an area that we can provide as input. So we provide as input an image or a distribution, we provide some meaning about the areas that we would like our robot to explore. And now we set it as a control problem that is asking how to explore that efficiently, how to move if I want to cover this region in an efficient way. And what I find fascinating with ergodic control is that it's purely deterministic. It looks random, and when we look at this result, it really looks chaotic, like there is something happening, while in reality, if you give the exact same distribution and if you start from this point, everything is reproducible. It's really like the optimal way for this initial condition to cover this area, which is a bit like disturbing. It's a bit puzzling, and it's why I think we like this technique, is to understand, like, mathematically what's behind. And mathematically it's beautiful mathematically. It's like making a mix of what we know as spatial description of the problem, and we need to move that to the spectral domain. So we need to think of this as frequencies, and this is what we like. I will first show you the applications that we have been using. So our application is to explore, like we would like a robot to search for an object. It can also be surveillance application if it's a mobile robot. It can also be rescue robotics if we want to search for someone, or in a disaster scenario typically. So it can also be to cover areas at a broader scale. For us, it's more about manipulation. In our group, we are specialized in manipulation. So for us, it's more about enabling a robot to cope with uncertainty. So if we don't know exactly where an object is, we can use these ergodic control techniques as a way for the robot to learn and to move around in order to find the object. So this is a sketch about what it's doing. So the input is a spatial distribution. The output is a set of control commands. Now, there is another category of problem also doing this coverage, also tackling this coverage problem. It's the one you see on the right. So on the left, it's the result of ergodic control. On the right, it's a much more patterned search problem. This one is good when you don't know anything about, if you know about the timing, So if you tell to the robot you have 20 seconds to search for a set of keys in this environment, then that's the optimal way to do. So if you know that you have 20 seconds, let's say, that's what you should do. That's what is optimal. On the left side, it doesn't say anything about the time. It just tells to the robot, find the keys as soon as possible, which is a much better description of the problem. So, if you think of that as a real-world scenario, like if you search for your keys, you are searching for these keys in this living room, then that would be completely awkward to do. You would never do that. You would never scan the table like this. You would do something like this. And algorithmically, it's very interesting what's happening when you do ergodic search. There is something related to frequencies. This is what we typically do. We start from a very crude search. So it means the low frequency component. So it's this very blurred image. Like we see the room as something very blurred. We see the scan that we do as also something very crude. And we first start to look like that. And progressively, we will add more and more frequency components. So we'll look more and more at the details. We'll have a finer search that will progressively happen. And this is what the algorithm is doing. It's thinking of the problem in the spectral domain by having these different levels of blurring, if you wish. And what is nice is you can let the system continue as long as you want. So it will just refine it using more and more frequencies and making the coverage being more and more precise. So this is useful for many applications in robotics. So the one that is the very industrial one that we cared about first was about insertion tasks. Here we have a robot that needs to insert this peg into this hole. It was here like a piece of gears that was a benchmark used for manipulation tasks. We had a sensor. It was not precise enough to tell to the robot exactly what is the entry point. And even if the robot would know the entry point, you still need to change the orientation of the gripper in order to do the task efficiently. Because maybe when you grasp the tool, you also don't know exactly how is this peg within the robot gripper. So you need this kind of search process in order to make the task efficient. And it's also much more cost efficient because you don't need to have a very expensive sensor to know exactly what's the situation. You can let the robot use this ergodic control to cope with uncertainty. So that was our first experiment. Then we moved that to some dishwashing experiment, where here we could play with the robot. We could actually like use a marker in order to draw something on these dishes, and have the robot like optimally covering the area, so trying to erase these marks, and sometimes coming back to these marks because we cannot really predefine in advance if it will really erase it. It's the same as when we wash dishes. Sometimes you will have something stuck and you need to come back to it. So this is exactly what the robot was doing here, as this optimal coverage problem. And by observing these movements, these patterns, we realized that there is also something to do with drawing. And here it was starting from an inspiration with the work of Patrick Tresset, who will present after. We are thinking, like, can we use these ergodic control algorithms as a way to generate paths in order to cover efficiently the canvas with a distribution. So for us, the distribution was the image, and we have then to make paths that would replicate the different shades of gray by just spending more time in regions that would be darker compared to the regions that would be lighter. And we compared that to different techniques. So that was at the moment, like in the research papers, you could find this technique called SMC. I will not enter into the details, but that was one way to do ergodic control, but we didn't find it very satisfying. There is also like the more generic, I would say, like stochastic generation of strokes. So there is also this category of work. And then there is another one related to ergodic control that we were very satisfied about, and we wanted to test that on a robot. It's also like there's also something nice behind that, is that there is behind this some kind of thermodynamics process. If you want, the image here is viewed as if it's like eating, like it's like a source. The source is like something that would eat. And then the robot is something that can cool down. And then when the robot is moving, it will actually cool down the areas that are warm. And there is this process, this underlying process that is also like interesting algorithmically. Like there is this link also to diffusion that we also cared about as algorithm, because we, in our group, we really, I would say, care about this modeling and algorithmic aspect. So as starting point, we took some work, like I would say we took back some work that was quite old now. I realize that it's 20 years now, so this work was 20 years old. We were doing that first without ergodic control, so this was much more patterned replication of curves. We called this robot at this time Salvador Dabot. It was making very small drawing, like it was like just 5 minutes drawing of portraits, with a process where we used ink that was very watery, so that if we make like several strokes at the same place, we could have different shades of gray. We had this kind of pattern that were circular, with this kind of small drawing. It was in some way mimicking what's happening if you are like putting like maybe your wrist on the paper, and making the stroke would make something that would be an arc. So we were like in some way mimicking that very crudely. And we started from that. So we have this kind of practical knowledge about how to make these drawings. And we applied this to, I would say, more modern robots where you can also control the force that is being applied to the canvas, that the workspace can also be much larger. And we wanted to test this ergodic behavior with these more recent robots. And we tested that in different settings. So we had one that was at a museum where we had some photo booth where the visitors could take their portrait, and we had the robot. Here you can see it as like 4 different canvases. So we had this thing running nearly autonomously in the museum. It was taking 1 hour per portrait, so it means we could make it run without human intervention for 4 hours. So for 4 portraits, people were queuing to get to this photo booth in order to have a portrait being drawn. And they could typically like visit the rest of the museum before picking back the portrait. We called it Drobot, and here it's a tribute to Pierre-Jacques Drault. It's the Swiss watchmaker from the 18th century, doing more or less the same thing. So that's fascinating that with automaton you could have this level of skills by assembling something without any electricity motors, but only by changing some mechanical cams, and to have this also portrait being drawn. So as a tribute, we use the name Drobot, and of course for draw as also drawing the verb. To help the system a bit, we also used some AI to detect where are the facial features in the image, which is giving information about what needs to be reproduced with more care. So to spend more time in these facial features than a detail of the shirt, for example. So it was also something behind the hood that was very important if we wanted to have realistic portrait. And with this, we could make this drawing application. So that's some of the results. Here is the one that were done at this event. So it was running during 1 year at this museum at Unilchuv in Lausanne. These are a few other examples. So what is interesting is what's happening at the beginning of the portrait, because you have people watching first something like that. So first it looks random, but as I was saying, it's purely deterministic. The movement itself is quite interesting to watch. We are a bit surprised that people were sometimes watching that for more time than we thought they would do. So it's also a sign that it's very different. They would not have stayed as long if it would be a printer. So the movement itself was very interesting, and we could collect like feedback also for this. So for us, in some way, this is a side project, but that we really enjoy. And on its way today, I wanted also to emphasize this. Another point that we care about is to, as I was saying, it's to really I would say on the didactic level, it's to provide tools for other researchers to understand the algorithms behind, and also to test these algorithms. So we did some effort in creating this web page, this website. It's called RCFS, for Robotics Codes from Scratch. And it's a way to interactively play with these examples. So there is a piece of code that is really like the minimum you need at algorithmic level in order to both understand and play with the codes. And these are like web page being interactive. So you have some examples being planar examples in 2D, some others being more elaborated with a robot that you can visualize on the browser. And here for ergodic control, we have many examples with this. So it's something that we use for the educational aspect, but that we also like to use internally for fast prototyping. So it's something that we are happy with. It's easier to use compared to a notebook. Like it's more minimalist version of a notebook. So it's also like, I should maybe mention that it's also in some way, at Idiap we have this long history of creating software libraries. And one of the examples that is well known is PyTorch. So people working in machine learning or data on computing in general, PyTorch is one of the well-known tools to do AI and machine learning. And before Python, it was Torch. So the backbone behind that is in C++ with Torch, and Torch comes from Idiap. So Torch is the research result from Idiap that has then been a lot of people have contributed to it. So we disappeared a bit from the picture, but we like that this origin was at in our small research institute in the Swiss Alps. So with this, so that's the persons behind these works. I like to show not only the current group members, but since there is a big turnover in research institutes and in academia in general, I like to really keep the list of all of the alumni because they also contributed to this work. And on the last video I wanted to show to you is this one. It's a very Swiss example of robot learning by demonstration and by self-refinement. It's called RoboClad. It's a special use of robots like it. We did that more as a way to communicate with people because it's not an obvious use of robotics. It's very disputable that we need robots in this kind of situations. But we had this very expensive device that was helping at doing a very traditional meal in Valais as the raclette cheese. And we had this ambassador that was helping us to cope with the communication aspects because he was the one telling that with the same technology you can make also like assistive behavior that are more useful than having this expensive machine. So with this I will conclude my presentation and I hope to have enough time for discussions and Q&A. Thank you.
We have questions already. Is there a link between traveling salesman problem and ergodic controls?
There is a link with the other one. So the pattern search that I was presenting is a traveling salesman problem. So traveling salesman, it means you know in advance how much time you have. So if you do this, you are in a category of problem that will result in something that will often be pattern search that are efficient. Ergodic control, since there is not this constraint of knowing the total duration, it's producing something quite different.
So thanks a lot for the presentation. So when you say like you teach robots by increasingly making things more difficult, that I think is exactly like, as you said, how humans learn probably as kids. But doesn't that require that the robot in general has like common sense, not to get like from the simpler task to the more specialized task without doing some unwanted whatever detours, so because this space, if it's machine learning, I learned that sometimes there's this problem that you never know what happens if you get to new regions of your space.
Mm. Yeah, thanks for the question. So we treat it in some way as a statistical learning problem. So there is behind something that is in some way a bit boring in the sense that it's a lot about counting and observing regularities and understanding these regularities. It can be in different space, in different coordinate systems. So it means there is always an underlying representation where we can get these regularities somewhere, while somewhere else there will be no regularity. So it's also about determining like which is the best observer space to find these regularities. Then the other challenging point is that these regularities can be both continuous or symbolic. Continuous, it means like when we have a movement, there's some part of the movement that is hard to describe as I would say as a discrete keyword. So you have one part of the challenge being really in the continuous domain, in the control domain. And another part is much more symbolic in the sense that we can describe it. It's something like a piece that is more discrete. And when we look at regularities, we need to consider both. If we consider only one, we have limitations. So to give you an example, if we would consider only the continuous level, then we would have a robot not understanding higher level concept. And that would have a hard time to reorganize part of the skill in a different way. It would be less modular. While if we would care only about very discrete blocks or symbolic blocks, here we are losing the movement aspect. So the robot is not really skillful anymore. It's more like a machine that doesn't really need to be physical, I would argue.
It's maybe like ourselves. We also have like this symbolic space to control or overall actions, and then we have this very delicate motor control of our fingers that do the rest, maybe. Yeah.
Yeah. Mm-hmm. And when I'm saying motor, it's it's more like sensory motor. So it's also like the way to cope, like depending on what we perceive, how to act on a different time scale.
Thank you very much. I was wondering whether there is an analogy to what we call body memory in humans and robotics. So if you look at the embodied learning process, like learning to dance, at the beginning you have like verbal things that you process, and then you have visual feedback, and then you consciously try to do the steps right. But at a point when you are an expert in dancing, your feet do the things for you. So it's kind of, the knowledge is kind of like incorporated in not only in your access knowledge, but also in your movement. You have to reproduce the movement to explain it to others and not just do it verbally. So is there something like maybe a difference between motor skills and the central processing unit, or something within the architecture of the robot that would distribute the computation? I sound naive, but do you understand what I mean?
Yeah. So to me, there are two very interesting aspects in your question. So one is about how to combine symbolic behaviors with continuous behaviors, and how to, I would say, reorganize this knowledge and communicate about this knowledge. So there is one aspect. And the other aspect that you mentioned at the beginning of your question is about how to adapt to perturbations. Like what will happen if there is something that is not expected? And also like how we can use automatism, like when there is something that is like a recurring pattern, how can I use that so that I don't need to be like in some way like fully aware all the time with my sensors about what's happening? Like what can I do in a feed-forward manner? So here in terms of control, there is this very nice, in some way, like mathematical description of this, where you have a control command having both a feed-forward part and a feedback part. And the feed-forward part would be what you can do automatically without thinking too much, like without having to use a lot of sensors, but what can I do that is automatized if I have a recurring pattern? And the feedback part is about coping with perturbations. And this one is more costly because you need to use really the feedback loop with the sensors telling what the controller should do. And what is in some way missing in research nowadays is to switch between one and the other in a more efficient way. So to have this kind of slider from fully feed-forward to full feedback. And this slider should be depending on what's happening with the robot. So like if I'm taking the analogy of driving a car, if it's your car, there are a lot of things that you do with automatism, or you don't need to think about it. But maybe if you now have a new car that is a bit different, you still have to rely more on feedback at the beginning. And when you have enough, in some way, data to make it as a feed-forward controller, then you can readjust this automatic behavior. So there is this kind of smooth switching that needs to adapt to the environment, to what's happening, to the amount of perturbations. And in robotics, we still have a lot of things to do to use that efficiently, at least trying to mimic what we do.
Can I add a very short comment? Maybe it's also a question of the architecture of the computation. So in philosophy, you always have this, people say everything is happening in the brain, you can transplant the brain, and we had this discussion yesterday, and most people would say, no, but this is a different body, or this is a different robot. So the same computation would not work in the same way in another kind of realization, material realization. And so if we say, okay, we need the whole nervous system, and these automated processes then are more located in the extensions of the brain, also in the extensions in the outside world. Is there also architecturally in robots something similar?
In some way, yes. And the way I would describe that with my engineering perspective would be to talk about these different coordinate systems. So maybe one simple example would be to say that I can have a robot where I can move the joints, joint angle level, so I can move it like this. But then maybe I will care about the location of the hand. And this is another coordinate system. So it would be to move from joint space to task space, so more as a 3D coordinate system. And here, very likely, if I have taught a task to my robot, maybe there is something that I can reuse in one of these coordinate systems, the task space one. Or maybe if I'm changing my robot arm, I can still reuse some knowledge that I have about this, but I won't be able to use the full knowledge. So the one related to joint angles is typically something that is hard to reuse, because if now I'm moving from a 6-axis robot to a 7-axis robot, then I don't know how to reuse this data efficiently. So there is, I would say, one way to rephrase this, but from an engineering perspective, would be to talk about different coordinate systems and to handle that in an efficient way. On this coordinate system, there is something we call that also like manifold. So there is a lot of geometry also behind to understand what we can transfer from one machine to another.
More. I really like those pushing and pulling experiments and also with tools, and I wonder, like, do you have to use a very precise inner kind of body model, like that the robot arm knows its own shape? Because I'm always worried, like you have this one like that you see here, which has a really wide nose, and that it has to be aware that if I want to move there, I will actually push that cube off. It's heading for the tool, but there's actually a cube in the way because. So it doesn't know about all its kinks and the boxes and stuff, or how precise do you have to be there? So
yes, so of course we do quite a lot of simplifications when we do these experiments. So robotics, there are so many components that needs to be tackled. Like there is to simplify, we could say it's like perception, control, and planning. It's an oversimplification, but even if we make this oversimplification, there are so many elements that needs to be considered, but very often, if we want to study one specific point, we will often simplify the other points. So to give you an example, like with this experiment that I showed, the one you were saying, we did many of this kind of simplification. So here the simplification, as you see, but in terms of perception, it's super simple. We have QR codes. So we are simplifying it at a point where we know where the objects are. In some other cases, we still have something a bit more elaborated to describe the workspace. It's more related to point cloud that will represent where are the obstacles, like to understand the environment of the robot. And in some other experiments, we use this, but it's still one maybe next step. But in all of these techniques, there are still quite a lot of simplifications that we do in order to study. So in this case, we know precisely at the level of the joint. We have encoders that are very precise to tell us where the robot is. This object, we also have in this case a model of the object. So we didn't include it in the learning phase, but we could have. So we make this simplification that the robot has access to this model. So then it means that it's viewing in some way its own body, with the tool being an extension of its own body. So we have this kinematic chain. You have the object, it's defining a new point of interest, and depending on where you grasp the tool, you will change your kinematic chain. So in some way, the robot is deciding how to make its own body if it wants to be efficient at doing the task.
So because I saw, you can change it. So there is a case it might just kick something over in this case when you just place the cube at the wrong position at the wrong time. Or would it be aware, like, oops, actually there is this little red stick sticking out at the side, and if I move this way, I have to actually move around the pile to avoid kicking it over with my own body.
Yes, so here we often consider like the obstacles indeed of the environment, but also the robot itself. So we need to consider both. And if it happens, then at least the generated movement is taking that into account, and then experimentally we often have like cases still like this that can happen, but that are related to.
Thank you so much for the presentation. I got a question that how was time considered throughout the process. For example, human running, if we have a deadline and with the unlimited time, the running results can be quite different. And not only about the results, but this kind of time controlling can be effective on the musicality or movement behavior of the machine and the researchers or the human beings. So I was very curious about that.
Yeah, thank you very much to bring this point. It's indeed a very important point, but sometimes is neglected. Sometimes we think of what the robots need to be learned as something that is really like spatial, like as a path. But in reality, there is a lot of time aspect at different levels. So there is the time aspect in what the robot will do as a movement. So understanding how dynamic the movement is, like what, how to modulate also this time. So to give a very specific example, just with the pick and place movement, like a very industrial pick and place movement. Then if my object is here, and if the arm is here, then the time to grab it should be shorter than if my object is far away. So it's first like a very simple example to show that the time should also be considered together with the path that we do. So there is the time at this aspect. And there is, after the time aspect, also in the learning process. So how long we can have a robot learning, how long the user should be here to assist the robot. And here it's a very complicated problem because depending on the assistance, if it's light assistance, maybe we can consider that the user is here for quite some time. If it's a very strong assistance, then it can be like just bothering for the user. So if we see that as tools, then we don't want to have a learning from demonstration mechanism that would actually take more time for the person to train a robot than doing the task on their own. So there is this timing aspect here that is very important. Also for the self-refinement, like if we have a robot learning on its own, like how long do we want it to do that? So ideally the challenge would be to have robots that can still do the task while learning. So that's the ideal scenario. So that the robot can start working in some way, like we can start moving, but while doing can refine. And here it's quite challenging algorithmically. It's easier to split the two, to say this is the time for learning, this is the time for deployment or for reproduction. But ideally we would like to have that much more intertwined as a process. And it's one of the research challenges that we have.
I would also relate to the question about time. In philosophy, we have this concept from Merleau-Ponty, the intentional arc. That means if I move, and this is not a symbolic representation, this is more body intentionality. I move and I have this present situation, which keeps a bit in mind what just happened, the intention, and we anticipate possibilities of where my movement goes. So my arm could move like here, it could move like here, and without making this explicit, it's always this anticipation of many possibilities is always within the situation of movement. So this would also be a temporal frame of movement. Is that something that can be somehow, if I speak of representation, it sounds again as like a symbolic representation, but is there something like that also in the computation of movement?
Yeah, so it is, but I would say there are also like a lot of ways to improve that. So typically what people will do as engineers would be to talk about model predictive control, where they would have some kind of time horizon that is looking forward in time, like what to do. But often what is not done correctly is that this time window in some way is a bit too much fixed. So for the control aspect, it will often be like predefined. And what is a bit missing is like if we think of a robot that needs to walk and do something, it will more look at the next step, but not really thinking of, for example, me who wants to go to the train station. It's missing a bit these different ways of scaling the anticipation like if I'm looking at a time window that is short, it's more likely something that is really like, I would say at a lower level than if I'm thinking of the way I will have to take a flight to come back to Switzerland. So we are much better at having this kind of different levels of representations that we have about what we should do next, while the robot is missing a bit this aspect. So we tend to think of model predictive control sometimes too much as a low-level component. I would say.
Thank you so much. I have a question about the image processing step. So you showed a few techniques and algorithms on how you trace the image to convert it into brushstrokes. I'm curious if there would be any difference in terms of the real-time vision versus image processing. Like my understanding that in this case you're pretty much converting the image or bitmap into vector graphics. Like from your perspective, obviously there is a difference in terms of the depth and all sorts of different physical properties between the captured image and if, for example, a robot would be deployed with some depth cameras and some other sensors. How would it play into the perception of the machine in terms of the vision, and how do you think this would help in translation of the painting language?
Yeah, thanks a lot for the question. So, you know what is a bit surprising is when we do tasks related to grasping and manipulating objects. So here we take into account the 3D perspective. So we will often start from point cloud that we'll know about, like how far we are from the different objects. And a bit surprisingly, when we move it to drawing, we tend to make it a bit more flat, which is not ideal. So it's something we should not do. So it's true that we often start from images. When it's portrait, we still analyze the image. Like we still analyze the content of the image. So in some way, like indirectly, if we know where is the nose, where are the eyes, in some way we are using an underlying perspective when we do that, but it's not as elaborated as when we are doing the manipulation task. So it's definitely something that we could use for this specific application. Then to come back to the part about vector, like image versus vector art, I would say still one more step, because a vector rendering would not really take into account the timing or would not view that as a trajectory. While in reality, it's not only vector art, it's that we need after to decide where to start, what kind of dynamic we want, how to move along this path. And here it can generate like movements that will be quite different. So this is a very important aspect, especially if we don't care only about the end result, but really care about the full process. If we are observing the robot, this will have a huge influence of understanding how to move from vector paths to movements on the real robot. And it's a part that is important.